Hello, ma'am.
Yes, can we start?
Yes, ma'am. Yes, ma'am. Go ahead. Uh,
A very pleasant morning to each and everyone that we have today in this event. On behalf of whole physics department of Kirodimal College, I, Ayushi Chauhan, would extend our warmest welcome to all the eminent guests that we have today, especially our head of the physics department, Dr. Rakesh Pandey sir, and our guest of honor, Dr. B.S. Shylaja ma'am, all the staff members, and my dear companions. Starting up on this 21st day of March 2023, we are glad to introduce a seminar talk organized by the Astro Club of our physics department. In today's gathering, we would like to focus on all our volunteers who have joined us and will make sure that all of you would get to know some of the new facts in this field of science. Being in the field of physics, we should all be deeply interested in the field of astronomy. All this field has a long history in Indian subcontinent stretching from prehistoric to the medieval times. And this astronomical knowledge in India can be traced back to the Vedic lecture. Indian astronomy flowered in the 5th century with Aryabhatta, whose work represented the principle of astronomical knowledge at that time. Today, through this science webinar, we all are gathering to know much more about this astronomical text. The topic for the webinar will be Instruments in Indian Astronomical Text. Before moving ahead, I would like to acknowledge the presence of our head of the physics department, Dr. Rakesh Pandey sir. I request you, sir, to please address the gathering.
Thank you, Ayushi, for taking the initiative for this program, and all the students, including Parth, also who took initiative. The teachers also who took initiative to uh, have this program with us. And first of all, I would welcome Dr. B.S. Shylaja, who is our speaker today and who is an established name in herself. She is well known for her contribution in popularizing science and in particular astrophysics. She is a former director of Jawaharlal Nehru Planetarium, and it was very nice for us that she agreed and accepted our invitation to have this online webinar for our students. This astronomy and astrophysics are so interesting, but so vast that it actually all the students, whether they are from physics or otherwise, also all of them take interest in knowing these things. And the topic today is so interesting that you would come to know that what all were being done in the era which we have forgotten. So those things we would also learn today and see today. The speaker of today is so known for her initiative and popularizing astronomy and astrophysics. She has, as a director of Nehru Planetarium, Bangalore, she has taken so much of initiative in taking conducting so many programs to popularize, and all her initiatives were very well taken by not only students of physics but outside physics also, for laymen also. So I hope that today's talk would be equally equally attracting for everybody. So let me welcome her and ask Ayushi to move ahead with the program. Thank you so much.
Thank you. Thank you, sir. Well, not taking too much of our time, I'd like to introduce our guest of honor. We are fortunate to have such a great literary personality as our chief guest, Dr. B.S. Shylaja ma'am. She joined the Jawaharlal Nehru Planetarium as educator in 1994. She has been involved in the preparation of planetarium programs and has initiated teaching astronomy workshops for universe in the classroom. An Introduction to the Night Sky. She initiated the monthly Skywatch program called Know Your Stars. She has written more than 300 popular articles and several weekly columns in Prajvani. Her monthly Skywatch column is running since August 1999. Dr. Shylaja ma'am has become the senior scientific officer, then deputy director, and took charge as director in 2012. She obtained her master's in physics from Bangalore University and PhD from Indian Institute of Astronomy. Her subjects of interest include comets, specular stars, and novae. She is currently working on stone inscriptions like translations and analysis of manuscripts in 17th century. Some of her publications include a Karana text on Siddhantic astronomy in Kannada, investing the astronomical histories of India and Southeast Asia, that is the role of stone inscriptions. It gives me an immense pleasure to welcome our chief guest. Please welcome such a talented and skilled personality, Dr. B.S. Shylaja ma'am. I request you to please join ma'am.
Thank you for that long introduction, and thank you for giving me this opportunity to address the youngsters who are so greatly interested in knowing about Indian astronomy. Because today is a special day, I would like to tell you about the importance of today, which is the equinox. And in the process of describing the instruments, you will also understand why today is important. I will conclude my talk around 12 o'clock because at 12:07 is the noon transit here in Bangalore. And we have some instruments outside in the park, and we will demonstrate the meaning of equinox using those instruments. These instruments are similar to the Jantar Mantar instruments you have in Delhi, but redesigned in a small scale for our latitude. So that is the program. So let me begin. So I want to share the screen. How do I do it? I want to share the entire screen. Are you able to see my screen?
Yes, ma'am.
Okay, so this is the topic I have chosen for today. What were the instruments that were used in India, say 1,000 years ago or 500 years ago? Because the telescopes, as you know, came into picture only after Galileo. Before that, people did make measurements, and what were the types of instruments they had? This is only a glimpse of what we find in the Indian Astronomical Texts. Now are you able to see the next slide where I have defined the basic units of measurements?
Yes, ma'am.
So the two basic things that you can measure are the time and the angle. So time is measured in so many units. Okay, these are the various units that you are familiar with these names. Similarly, angle, these are the only two things that you can measure. And the measure of brightness, of course, came later only in the last 200 years or so. Before that, the entire astronomy was dependent, development of astronomy was dependent on the measurement of these two, namely time and angle. And it depends on how accurate you can measure this. So, Ahoratram means 24 hours, as we understand today, which was divided into Muhurta, which was called 30, or Ghati, which is 60. Therefore, one Muhurta becomes 2 Ghati, and so on. And Ghati was subdivided into Nadi or Danda, and then Pala, Vigati, Nadi, Pare, Tatpare. Tatpare, that way takes you to the fraction of a second. So they were able to compute up to the fraction of a second. Whether they were able to observe that accurately or not is a different thing, but then they were able to compute to that extent. Similarly, you have angle as degree, arc minute, and arc seconds, as we know today. So degree is either called as amsha or bhaga, arc minute is called as kala, and arc second is called as vikala. So these were the units you find they were using, and you will find the reference to them in almost all astronomical texts, right from the days of Aryabhata or even Shulva Sutra or even earlier. Okay. So then how did they write their numbers? This is something very interesting. The notation of numerals. Are you able to see this slide? Are you seeing this slide?
Yes, ma'am.
Okay, so they were, see, Aryabhatta had developed his own system, but the others followed very interesting method. For example, you want to write 1944. So this is written as Veda. Veda is the first word here. So Veda. Veda corresponds to four. Four Vedas are there. Then Veda again. That means another four here. Then Ka. Anka. Anka means there are 9 digits, 9. And Chandra, there is only one moon, so 1. So if you write a word like this, Veda Vedanka Chandra, it means 1944. So this is how it is written. So similarly, if I want to write 600, then Kha. Kha means 0. Kha also means the celestial sphere. Okay, Kha Gola. Now, Kha, Kha, 2 zeros, and Anga. There are 6 organs in the body, so that 6. So this is called Bhuta Sankhya system. That means you coin a word so that the word that is used there represents a number. So for number 2, you can use I, because there are 2 eyes. Or you can use Bahu, which means there are 2 shoulders, 2 arms, and so on. And similarly, if you want to represent 1, there is only one earth. Ku. Ku means earth. So similarly, the words were coined, and this method is called Bhuta Sankhya. This was very popular, and this removed all the errors that you encounter in making measurements, in writing down the measurements. Then you have another interesting system called the Katapayadi system, where only one letter is used for understanding the number. So here, for example, Ramaloke. So suddenly you will come across the word Ramaloke. Why Ramaloke? Where is this Rama coming from? So here, Ka, this is as per the alphabets in the Sanskrit language. So you have Ka, Ka, Gha, Gha, Nya, all representing 1, 2, 3, 4. Then Cha, Cha, Jha, Jha will be representing 5, 6, 7, 8. So similarly, Ta, 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 Da, Da, 1, 2, 3, 4, and so on. Similarly, Ya, Ra, La, Wa also 1, 2, 3, 4, and the remaining numbers are seen. And then the consonants Na, Ma are used for a 0. So here Ramaloke means Ka is 1, Ya, Ra, La is 3, Ma, Papa, Bha, Ma is 5, and Ra, Ya, Ra is 2. So this represents 1, 3, 5, 2. So Mecha means 65. Mecha is also the name of a raga in music. Mecha Kalyani, that's the name of the raga. So it is the 65th in the list. Then the word Vidwan actually means 44. And then you can construct a long word like this to represent 2735747. And this is the way the numbers were written. This is important because you will come across these kinds of notations suddenly, and you will not understand why Ramaloka or Mecha should be coming suddenly in between. Okay. And there is a special method attributed to Aryabhatta, which is much more complicated, which I don't want to explain. But you can read it if you get access to Aryabhatiya. It's a very complicated system. Now, this is not part of my talk today, so I will continue with the instruments. So here is the basic instrument. This is called a Shanku. So you are Yashti. So all people were using a 12-inch stick, OA, this one. And then it casts a shadow, and the shadow length is OB. And this OB is the thing that they were measuring. And because you know this 12, so they were able to compute the angle of the sun from the zenith. Okay, so this is simple trigonometry. And they had names for this. OB was called Bahu or Koti, and then this was called Yashti or Shanku, and this was called Akshakarna. This was called Akshakarna. Okay, you will see such things in Jantar Mantar. So this is the basic principle. So here you have a method of drawing the north-south point. So you draw a circle. This is the basic circle you have to draw, and just put a stick here and mark the position of the shadow once in the forenoon and once in the afternoon. And if you join those two, that will give you the east-west line. then bisect it, you get the north-south line. So this was the procedure that was adopted. And when you measure it today is the equinox day, you get the latitude of the place. So today is important because you measure the shadow when the sun is transiting, then you get the this angle which measures the latitude of the place. So for Bangalore, we get a different value. For Delhi, we will get a different value. And this was standardized. And this was called as Palabha. Nowadays we write for any place what is the longitude and what is the latitude. But those days they would write in the text, I have calculated this for Palabha. That is this value. And today in the modern text, you find that this is the explanation given. Earth is a sphere, and this is the tangent, and this is the angle it is making, and so on. Okay, so this latitude is same as this latitude. Throughout the year, if you were to put a stick and mark the shadow, this is how it changes. So this is the shadow on December 22nd. This is the tip of the shadow, how it moves on June 21st. Okay. This is for a place like Bangalore, but for Delhi, the pattern will be completely different. So here is one. This is in Ujjain. Ujjain, they have put this Shanku Yantra, and you can see these markings that are done here. Okay, so these are the markings. So if you have calibrated this for the year, then you get the date. And for the first thing they have to do is to mark the latitude corresponding to it. So they would have done that, and the rest of the things, either you can compute and mark, or you can simply observe every day and mark these curves here. So this is one method for finding the time and angle of the sun. And for longitude, they refer to a correction called Deshantara. Generally, all books are written for Ujjaini as the standard. And depending on whether you are to the east of Ujjain or west of Ujjain, you will have to apply a correction. And the unit is given in terms of yojana. Yojana is approximately 5 miles, they say, but then it varies. And for every mile, the time difference will be 1/80th of a ghati. So this is the definition that is given. So accordingly, we'll have to apply the longitude correction also. So this was very well known. So once you know how to measure, then these are the corrections that are essential, because you are not sitting at Ujjain and the text is prescribed for Ujjain latitude and longitude. So these are basic definitions of trigonometry. So this is the sign. Ja is called the sign. Always they express it in terms of a constant R sign, which has its own advantages. So cosine is referred to as kotijya, and there is another thing. So you have this is kotijya here, this is jya, this is jya, and the inverse of that is this angle which is called as arc, chapa. And this is the adjacent side, which is called as kotijya. And you have another, not the tan, but this one. This is called utkramajya. So this is also defined. This is a very interesting thing, and it has very interesting applications also. So as you can get from this, this is 1 minus cos. Okay, so here it is, utkramajya. So R cos plus this Utkramadja is defined in English as worst sine ratio. So this plus this is 1, that's the meaning. And R is the radius of this circle. And usually that is taken as 120 units. And the coordinates that we have here are well established even in modern positional astronomy or spherical astronomy books. It's the same things that are given. So you have the celestial equator, which is perpendicular to the polar axis, the north-south axis, rotation axis of the Earth. And in all these cases, the assumption is that the Earth is at the center of the universe and everything is rotating. So the diurnal motion also is taken care of. And this is the plane of the horizon. This is the plane of the horizon. And you have the east-west points. Today, because the sun is on the equator, it will rise exactly at the east point, goes to the meridian at 12 noon, and then it sets here at W. On all other days, it will not be rising at the point called east, it will not be setting at the point called west. It will be in the direction, but it could be slightly to the south or north of this point. So now let me tell about the instruments. I have picked up this text called Siddhanta Shiromani by Bhaskaracharya. It was written in the 12th century. Bhaskaracharya, as you know, was a very versatile astronomer, and he begins the chapter with this introduction. Since it is not possible to measure small intervals of time after sunrise without using instruments, I explained the use of these instruments. See, look at the list of instruments. Nadi Valaya, Yashti, Shanku, Ghati, Chapa, Phalaka, and so on. Then there is one more instrument called the Dhi Yantra. Dhi Rekam, that's in Dhi Rekam. Dhi means intelligent. I will just explain how intelligent that instrument is. So this is the Gola Yantra, which is a replica of the celestial sphere with all those circles, imaginary circles of the celestial equator, the horizon, everything marked here, so that whatever measurement you do in the sky can be converted into any other coordinate system that you can think of. So here, the circles that are shown in the white are the ones that are measurable, and the interpreted ones are the ones inside. The inside you have gray colored ecliptic, equator, and so on. These are the celestial coordinates. And of course, this is the north-south axis around which it rotates. Then there is a Gola Yantra in Mysore. This is how it looks today, and this was being used for teaching till about 100 years ago. And they have preserved the instrument, and this is also described in this online catalog prepared by Professor S.R. Sharma, who is very well known for his work on these instruments. Not only these kinds of instruments, but the astrolabes also. It's a 3,000-page document, and this Mysore Gola Yantra also finds a place in that. And then there is this instrument called Nadi Valaya. So what is the Nadi Valaya? So here the working of the instrument is described, and how the instrument is used for fixing the ascendant, that is also described. What we have as Nadi Valaya in Jantar Mantar is slightly different. This is how it looks. This is in Ujjain again. Ujjain and even Jaipur has this instrument. This is a fairly large instrument, and here you can see a person here, so you get an idea of the scale. We first got a tabletop of that made here for our latitude, and you see it is equatorial plane, so all the lines are marked here. And we got one constructed in our park, which will be shown to you just now after the lecture. So we got three instruments here. One is this Nadi Valaya, which is in this corner. This one is called as Dakshinottara Vitti. And then here you have the Samrat Yantra, which is so small, a very small one compared to the one you have in Delhi. So this is the Dakshinottara Vitti. Okay, so this is, because there are people sitting here, you get a feel of how large it is. So if this is the north-south, and whenever any object is transiting the meridian, that is, it is on the zenith, then there is a peg here, and a thread, and a viewing tube, in case you are observing in night. If you are doing it in day, it's easy. The sunlight will pass through the tube. So you can measure the angle along this. But if the object is on this side, you can use this scale. Okay, so this is how the measurement is done. We modified it slightly, which will be shown to you outside. And see, this was taken last March. So here, when on March 21st, you will see the dot here exactly at 0 point, because the sun is on the celestial equator. And all other measurements, if you want to do, this scale is calibrated here, and so you can take the measurements. And how to measure the time? This is the Indian water measuring device. So here you have a small bowl, into which another smaller bowl is inserted, and this bowl has a hole. So this dimensions of the hole and dimensions of this are provided. So when you let it float here, water will seep through this hole and then it will sink. And the time it takes for it to completely sink into water is a unit of time. So this is how it was measured. The time was measured. This is slightly different from a sand timer or any other such device. So this is the measure of Ghatika. So they had bowls of different sizes. And in one of the forts here in Karnataka, there is a very large tank which was used for counting intervals like 3 hours or 4 hours. And this instrument is called as a chakra yantra. The advantage is that this is oriented. This is tilted, as you can see, to the rotation axis. So this disc moves along the plane perpendicular to the rotation axis. So you can measure as it is moving the different angles it is covering from sunrise to coming to the meridian and from meridian to go to the west. Okay, so there are many other devices. I will not spend much time because this involves a lot of calculations called the Chapa, Turya, and Palaka. Chapa is like a quadrant here. This is a very simple thing that perhaps you also have made. You have to drill a hole to your protractor and put a drinking straw. And if you view through this any particular star, then the angle it makes here with this thread tied here, that gives this altitude. So this is a very simple measuring device. So basically you are seeing, so this is the vertical, so this gives you the angle it makes with the zenith. So this is one thing that you can very easily do for night sky. Okay. Now, a similar instrument was used in Europe. See, this is a famous astronomical observatory of Tycho Brahe. He also was using an exactly similar instrument. And so here is the dial. Naturally, you can see that if you use a small protractor like this, your accuracy will be 1 degree. If you use something like this, it may become half a degree. And if you use an instrument like this, you can improve on the accuracy. And then they used to have smaller gadgets, 1 year measures here attached, so that they measure the angle very accurately, which is possible for stars, not for the sun. And then we have an instrument called Palaka Yantra, which is very complicated thing. So this is the description, but here it is. You know, what you have to do is you have to create this phalaka or the board as per the instruction, and then measure the shadow. And you have some calibrated circle given here, so the shadow will give you directly the time of the day. Otherwise, you will have to do some corrections for the time depending on the time of the year. So how to construct this graduated circle so that you get the reading directly. So this is the ingenuity of Bhaskaracharya, and he has described this instrument in great detail. So I tried this instrument, but I will not spend time on explaining it. So this is the construction procedure. Every fine detail is given. If somebody is interested, they can look up and create this instrument. It's patience that is important, because for each day you will have a different circle. And this is Palaka Yantra, how to use it. All these equations that we have from trigonometry are incorporated into the reading of that instrument. Okay, I will not spend this. So he also describes the usage. So I did this calculation for Bangalore, and then I used the differences, and finally I measured it with a device here. For April 5th, from graphical construction, I got the hour angle as 41 degrees. And from the formula that we have from trigonometry, I get 40.1. So similarly for some other day, when delta was 5.9, the difference is very small. So this is a very interesting instrument described by Bhaskaracharya, and somebody can try this out. And when you come to sundial, it's a very popular thing. At least in Europe, you will come across several sundials along the road, in gardens, in houses, on buildings, on public structures, and so on. But here is one in Kanyakumari. This is one in Kanyakumari. Many of you might have visited. So if you go to the Vivekananda Memorial Island there, then you can see this from the top. So it says sunrise calendar, and then they have marked for different days. On the you can view it from the top. This has been done recently, I think maybe in the past 25 years or so. There is a confusion on Uttarayana and Makara Sankramana. That is reflected in this drawing. See, this is December 22nd. This is December 22nd. This is marked as Uttarayana. Okay, but then they have marked it as January 14th. So that is the mistake. But the sun is not to the southernmost point on January 14th, but on December 22nd. So these are the different dates for which they have marked it here. So if you go and see the sunrise at Kanyakumari Island, then you will be able to verify whether this is true or not. Yashti yantra, as I mentioned earlier, is a very simple stick. This is a simple stick. What you measure is only the shadow, and then the shadow represents the angle as well as the time of the day. Okay, so how to construct this is explained here. So the application. So what are the applications? You can find the latitude of the place by two shadow measures. Now today, if you do the measurement, you can get it instantaneously. You get the latitude of the place. But if you want to measure the latitude on some other day, then you have to take two shadow measures, and how to compute the latitude using that is described in the text. So then you find the declination, and that is the north-south coordinate of the sun, the time and latitude of the place by three measurements. So if you want to get the declination of the sun, you need three measurements. And the method is proved, and he argues that the statements of some of the predecessors on this are wrong. This is a very important thing because this shows that they were using these instruments continuously and were trying to verify the veracity of the declarations of the previous authors. So this description in Bhaskaracharya's book very clearly indicates that they were doing this very accurately, and he gives the alternate procedure for that. And there are hints on correction for precision. Okay. And then there are many examples of using these instruments. So in a place, no, this is one question that is posed at the end of the text. In a place of which the latitude is unknown, and on a day which is unknown, the sun was observed on entering the prime vertical. Prime vertical is the 45 degrees, this thing, giving a shadow of 16 digits long at 8 ghatikas after sunrise. If you will tell me the declination and the palabha, I will hold you to be an expert. So this is the question that is posed at the end of the chapter. So one has to be very clever to decode the meaning of this and get the declination, and palabha means the latitude of the place, by just using the fact that you have made one shadow measurement and you have the other information that it is on the 45 degrees circle. Then here is another example of the question. When the sun enters the prime vertical of Ujjain, either at 5 ghati after sunrise or 5 ghatis before or after midday, what are his latitudes? So he is not at Ujjain, he is elsewhere. And the question is related to Ujjain. If you will answer this, I will hold you to be the sharp ankusha for the guidance of the elephants. Now, ankusha means something that is very sharp. This is a small tool used by the people who guide the elephants. The yantra, you think that the yantra is a very, very important instrument. You should not imagine something very huge. It is just a tube. It is just a sighting tube. So here is the description. So it is an intelligent instrument because he describes what are all the different applications of this. So he says you can use this to find the latitude of the place. How do you do that? Very simple. You use your height for this measurement, and then you look at the pole star. That's it. It's a very simple thing. But you shouldn't be carried away by the word yantra. And then there are many solved examples of using this yantra. Okay, so here is one. You want to measure the height of this. You want to measure the height of this. So, and also the distance to this. So he makes a measurement like this, finds out what is this angle, what is this angle, using the tube that he is holding in his hand. That tube length he knows, and he can only measure this. So this is a simple extension of the property of similar triangles. I will give you one more example. So the length of the sighting tube is 145. There is a bamboo on the opposite side, and this is the solution. So here is a bamboo. So he says, what is the height and distance of the bamboo? So these are the two different sticks he used. He knows this and he knows the base. He knows this, and therefore he solves these two and gets this. Now, this is a simple application of trigonometry. Now the same thing he uses for getting a simultaneous equation also. Two sighting tubes of different lengths, so that the quotient is one. That is, the cast should be same. The opposite adjacent side is the same. So bottom of the bamboo is not visible. So how will you calculate it? So again here he uses the same trick, and then he gets the answer. Okay, so these are very interesting problems that are posed in Siddhanta Shiromani. And then there is one more application of using simultaneous equations. So here is one. Here is a person looking at a tree, and he sees the reflection. One's standing, one's sitting. Once when he stands, he knows what is the angle he is measuring. So these numbers are given. And this is converted into a simultaneous equation. You get the distance of this plant and also the height of the plant. So here it is. This is using reflection in water. So you have one set of equation, which is 11 by 8 is equal to this. And then you have another where you have a different equation. You solve the two, and you get the solution. Okay, so don't worry about the units. The units can be something which was prevalent those days, but just using a stick and measuring the angle, you are able to solve these kinds of problems. These are terrestrial problems, and it had applications for the planets also. For example, for measuring the altitude of a planet. So you look at the reflection and then measure the altitude of the planet. Otherwise, you will have to strain your neck. See, you can't be looking up all the way. Okay, so these are the examples. And then he describes a very funny instrument, which is the Swayam Vahana Yantra, something which moves on its own. This is an instrument which was described by various people, and Bhaskara repeats it. And he states that he describes it simply because his predecessors had mentioned it, but he says that this is not possible. Something cannot be moving on its own. He criticizes and says this is only sapeksha. That means it is dependent on something. So the motion is procured by a trick. They are not connected with the subject matter under discussion. So he closes the verse here. So he knows very clearly that such an instrument, perpetual machine, which it keeps running without any energy provided to it, is not possible. And he describes the principle of a siphon, which we all have learned in our school days. He says he may make a copper tube or other metal and bend it in the form of ankusha. What is ankusha? Ankusha is the trunk of an elephant, like a U-tube kind of a thing. Fill it with and close both the ends. Then putting one end in water reservoir, let the other end remain suspended outside. Now unlock both the ends. This is the method that is given, and this is the same thing we all know about. So we were doing this experiment when we were in school. So we take a tube and fill it with water, close both the ends, and dip carefully so that no air leaks into it and into water. Then this whole water is drained into this. And he says this is a trick that is used by people for various things. They in public places, perhaps in fair or some such place, people would use this, and they will talk forcefully so that the exact principle is not obviously seen. So roadside magicians, they were using this. So he calls this a very tricky instrument. And then how do you measure the time in the night? For this purpose, in South India, I will come to that later, but in North India, this was the method used. You can see the 7 stars of the Saptarshi almost from all places in North India, almost all through the night. And so this was used in an instrument called Dhruva Brahma Yantra. So you have here, this is the small bear or the Ursa Minor. Use these 2 stars for finding the angle. So find the angle this makes with the horizon at sunset. And measure this angle again at any time of your interest, and that angle tells you how much it has moved. And for measuring that, this was the instrument. This instrument is there in Jaipur. So this was the instrument that was used. So this is very popular in Europe with amateurs, because even in Europe and the US, you can see this all through the night for those latitudes. And so these are the hands of the clock. They make clocks to go with this. And amateur astronomers also use this method to align the telescope to the pole. You know that the pole star is not at the pole. So to make use of that small thing, they use this idea. See, they make a device like this and fix it onto the telescope and ensure that the telescope is properly aligned to the north, not north. Well, we get to know that such things were observed and marked from an unusual calendar of the 17th century. And you see this mark here, this mark. This mark corresponds to the observational indication. And you have many astrolabes for different things. I had mentioned about Professor Sharma's catalog. It describes so many things. And these are quite complicated, and it takes a while to understand the functioning of this and how to use this for getting the local time, sidereal time, sunrise and set times, planetary visibility, all those things you can do with this handy instrument. Well, in South, they were doing the measurements in a different way. No, this is a very simple 6x4 card, wooden board, into which there is a hole and then there is a thread with knots. This was used for finding the time of the night. How did they do that? No, it's very interesting. You have several knots here on the thread. And then when you see the pole star from the edge of this, and then find out which is the knot which matches for that elevation. And then that is calibrated. So somebody is sailing from, say, Kanyakumari northwards. Kanyakumari, this pole star is very low. But by the time he comes to, let's say, Goa, then he can measure this and say, now that I have reached this height of the pole star, I can turn right and I will reach the port. So this is the way they were using the stars for navigation. And this is a map of navigation navigators used. And you see the numbers here. This is from Gujarat. This is the Gujarat coast. So they had marked at which points these places were. You have to take a turn to reach. The names of the places are all indicated here. And this was a map used by the navigators. See, they never went into the deep sea, but then they knew that if you go travel this way, you will come across so many small towns along the coast. Of course, now this is the most modern instrument, I should say, which uses a celestial property. This is in the Raman Research Institute here in Bangalore. All of you have heard of C.V. Raman. C.V. Raman's experiments needed a source of light. The source of light was the sun. But then his spectroscope was inside the lab. So how do you get the sunshine into the lab? So he had fixed a mirror, this mirror. This is the mirror, and you see it's a very interesting gadget. And I think some people can recognize this. This was the clock we had some 50 years ago. We have a spring wound clock. So here is the key. So if you wind it, it will run for a day. So this is how this was a very famous clock. And to the shaft of that, this instrument was attached. And nowadays you have a motor, but then this was spring driven. And this would drive this, which in turn would deflect this. That means this would be kept on the window and it will track the sun using this spring. And as the sun moves along in the sky, the mirror will track it so that the reflected light is always available for the spectroscope inside the room. So this was a very standard procedure, and in all solar observatories all over Europe or even maybe US, you will find these kinds of gadgets because this spring wound mechanism was a very useful tool, and they would adjust it so that it tracks the sun. The tracking rate is almost same as 1 degree per day, and this also is about 1 degree per day. And the gear mechanism here, they would adjust. Well, people knew that the sun moves at different speeds at different times of the year. Why? That is because of the elliptical orbit. Even corrections for that had been incorporated. And the orientation, sometimes the sun is towards the south, sometimes it is towards the north, sometimes it is, as on today, it is exactly at 0. So all these corrections were incorporated. So I'm concluding the talk with this because this was the state of affairs 70 years ago. Now you have electricity, you have GPS. It's difficult for you to imagine the plight of the people who wanted to do serious experiments those days. And these kinds of ingenious ideas were developed here. Okay. So now I'm thanking or paying my respects to these individuals who have done the pioneering work on understanding Indian astronomy in the period after independence. So you have K.V. Sharma and Krupashankar Shukla and Ohashi, Japanese, who spent his time in Varanasi and understood the meaning. Professor Asi Gupta, he is still active. He is still seriously studying the mathematics. And S. Balachandra Rao has contributed immensely. And there are many more names that I should be adding here. The group from Chennai, Professor Sriram Srinivas and Professor Ramasubramaniam, and so on. But now many people are showing interest, and this is coming up. This is a very interesting field for you to take up. So you will get these kinds of instruments not only in India, but you will find traces of them all over Southeast Asia. So that is very interesting. So I mentioned it because I did not want to miss this point. Okay, so thank you for the patient listening. If you have any questions, I will answer. Otherwise, we will go to the field and see the. Now, Anand is actually showing you the instrument already. That is the Dakshinottara Bhitti. At 12:07, you will be seeing the shadow. I think it's slightly cloudy today. In any case, Anand may want to say something about the. No, he's taking it closer. But is the resolution sufficient for you to see? Now, see. Now you will see the spot at the 0 point there. Anand, can you hear me? Anand, can you hear me?
Yes, ma'am, I can hear you.
Now you first show the long shot of the instrument, the complete
Yeah.
instrument, little far away. Is it there now? Is it cloudy?
Yes, ma'am. I'm mad.
I don't know. It is now looking vertical, but actually it is horizontal. You may have to turn the camera.
Okay,
Now,
this way I can't come.
okay. Now if people will get an idea of the instrument. So now you go little forward and take it to the scale. Okay.
So this is the Dakshinottara Bitti instrument you are seeing.
Hmm.
So I'm just closing down. There is a hole here. You can see the hole here. This one. When the sun comes to the zenith, the light passes through this, sunlight passes through this hole and falls on the scale that is given here. Okay. So today, actually, you can see that when the sun comes to the zenith, you will see that the the light spot will fall on this zero marking, indicating that the declination of the sun today is 0 degree. So we will wait for that and see, try to observe that in a while.
In the meanwhile, you can show the globe because we have 3 more minutes.
Yeah.
We have a parallel globe.
So this is a sundial, the Jantar Mantar.
Samra temple. This is a Samra
this is a
temple.
Samra temple. So aligned towards the north.
Right now you will not see the shadow because the sun is on the meridian. So you can't read the time right now. You cannot read the time on that right now.
So this is the globe.
This is the globe. This is called a parallel globe. And we have adjusted so that Bangalore is on the top. So this is exactly parallel to the earth as we see now. So when they are, when they, on the day of equinox, you will notice that the entire globe is illuminated. North Pole as well as South Pole, both are getting illuminated. So
I'll show you. This is the North Pole that you are seeing. You can see the North Pole is sunlighted. I'll go to the South Pole now.
the South Pole is also getting the light today.
So you can see that
Yes.
this is the South Pole.
If you were to see this, say 3 days ago, South Pole was getting the sunlight, but not the North. This also tells you where the sun is rising, where the sun is setting, and so on. Okay, that's the advantage of this. So as you can see,
Little. No, actually, uh, the sun is, the Earth, our India portion of the globe here is at the top.
at the top.
And so that the sun is exactly above that. So we have kept that. It will actually indicate the other things like where the sunset where the sunset is happening right now, what places on the globe, and also the sunrise where the sunrise is happening right now.
This is not yet rising at England. It's still below the horizon. But in Saudi Arabia, it is already up. If you go to the side, you can show. Now here, it is setting already. The sun has set already in Australia and about to set in Thailand. Okay, so that is the marker. You can very clearly see that the entire globe is illuminated uniformly. And if you see it 6 months later, you will easily see the difference. Okay. Now
I will go to the
huh.
and go back to the Nadi Valaya.
This is a scale model of the solar system. This is the Samrat Yantra we have. And we also have Dakshinottara Bitti. And now this is the one. Now you can put your hand and show how the looks.
That's one. So I will just zoom in and zoom into the scale where actually on which the spot is falling on. So can you see a dot here? Right? The sunlight comes through this.
Another 3 minutes.
Yeah. And now you can see that.
It's there. It's on the red portion. In another 3 minutes, it will fall exactly onto the zero. Okay. That's the meaning of equinox.
Meanwhile, just take one more minute to show this one. This is
This
is the Nadi Valaya.
You turn your thing 90 degrees. It's showing as vertical.
Sorry.
No. Okay, this is Nadi Valaya. This has the plane exactly in the plane of the equator, so there is no shadow today because it's in the plane of the equator. So you can't use this dial for reading the time. Neither the northern disk or the southern disk is able to give you any shadow readings.
Coming back to this scale.
See, now it is approaching zero. Equinox is an instant. Therefore, it will cross the meridian maybe at 4 o'clock today or maybe at midnight. It can change. So, we can only show that it is very close to zero right now. Maybe after 2 hours, but then it will not be at the meridian for Bangalore. It will be at the meridian for some other location. So now we can see that the spot is exactly at zero. Perhaps you can go to Delhi Jantar Mantar and verify it tomorrow. Tomorrow also it will be very close to zero. Okay, 12:07 was the time. I think it is exactly 12:07. I think we can stop there because thank you, Anand. Okay, so thank you, Ardra. And if there are any questions, I will answer. Thank you. Are there questions?
Good afternoon, everyone. Myself, Gaurav Joshi. Thank you very much, ma'am, for your
for this amazing talk. Actually, I was wondering that uh, in ancient India, when they used to make these measurements about time and date of the year, these might be have been helpful for the cropping seasons, and they might have also been helpful, like um, in the earlier times, as well as they used to sow crops at a particular time of the year, which would have been guided by this. But did they ever? My question is, did they ever wondered what causes this periodicity in the motion of the celestial objects?
Okay, the mathematics part was very well known to them. The mathematics part was very well known to them. They had their own way of understanding how all these things move. Okay, the idea of the sun being at the center and the earth going round, etc., all such ideas were not there. But then what you see sitting at this thing, they were able to explain it mathematically very clearly. So they had a clear understanding of the movement of the planets. When I say planets, I also include sun and moon, because the word graha means anything that is moving against this stellar background. So even the sun and the moon, and even this point of intersection of the orbit was considered a planet. So they said that all these things are moving, and they precisely knew the movement. Well, why? That question did not come. That question they haven't. They say that there was a pravaha. That means something is pushing them. This is the kind of argument. You will just see phrases like this here and there. But no, Newton's theory, etc., all such things was not there.
Thank you, ma'am.
Any other question?
थैंक यू मैम। अब कार्यक्रम के अंतिम चरण में मैं पार्थ जोशी धन्यवाद ज्ञापित करना चाहूंगा आदरणीय डॉक्टर BS शैलजा जी का, जिन्होंने आज अपना बहुमूल्य समय हमें प्रदान किया। साथ ही भारतीय खगोल विज्ञान एवं विषुव अर्थात इक्विनॉक्स के विषय में अत्यंत रोचक जानकारियां प्रदान की। हमारा पूरा कॉलेज परिवार आज आपकी उपस्थिति से अत्यंत गौरवान्वित महसूस कर रहा है। अपने ज्ञान रूपी प्रकाश से आज आपने अत्यंत सहजता एवं सरलता से हमारे अज्ञान रूपी अंधकार को दूर किया। अतः हम सभी आपका हृदय से धन्यवाद ज्ञापित करना चाहते हैं। मैं धन्यवाद करना चाहूंगा आदरणीय डॉक्टर राकेश कुमार पांडे सर को, जिनका मार्गदर्शन आज हमें प्राप्त हुआ और जिनके परिश्रम के कारण यह कार्यक्रम अत्यंत सरलता से संपन्न हो पाया। मैं शुक्रिया अदा करना चाहूंगा समस्त गुरुजनों का, जिनकी उपस्थिति से यह कार्यक्रम और अधिक रमणीय हो गया। कार्यक्रम समिति से जुड़े समस्त कार्यकर्ता भी अत्यंत अभिनंदन के पात्र हैं। एवं मैं हार्दिक धन्यवाद करना चाहूंगा आप समस्त श्रोताओं का, जिन्होंने अत्यंत तन्मयता से इस ज्ञान रूपी अमृत का आज रसास्वादन किया है। इस उत्सव के प्रयोजन का वाचन करते हैं, दिल से एक दूसरे का अभिवादन करते हैं। इस उत्सव के प्रयोजन का वाचन करते हैं, दिल से एक दूसरे का अभिवादन करते हैं। ऐसे ही बूंद बूंद बनकर खुशी का सागर बनाते रहें, इसी दुआ के साथ इस कार्यक्रम का समापन करते हैं। थैंक यू। थैंक यू।
Thank you. Namaste.
Thank you, ma'am.
Thank you.